Good. Hello? Now it turned red for some reason. No, now it's green, so you should be able to hear me. Okay, so I'm going to talk about the Zwicky Transient facility and concretely about how we're using deep learning for some applications with the Zwicky Transient facility, namely to do real bogus classification and identification of fast-moving objects. ZTF has been mentioned today already a few times, but just at a glance. So nice. So we're at the 48-inch Schmidt telescope at Palomar. We have a huge camera with a huge field of view, 47 square degrees. So this is our field of view. For comparison, this is LSST. We're capable of imaging the entire northern sky in one night and in a filter, and we get down to these depths, 5 sigma depths, with the nominal 30-second exposures. The primary science focus of ZTF is all sorts of transient science, but it's also great for all sorts of variable science and solar system as well. So this scary slide shows the ZTF data and the processing flow, but what's relevant for us here is this red box, which is the real-time image subtraction and source extraction pipeline. So this is the thing that generates transient alerts that get sent out to the rest of the world, and it also generates streak candidates for solar system fast-moving objects. And we generate an order of 1 million alerts, and something like the same for streaks as well. So, thanks to the previous speakers, you've already heard a lot about that. So you know what that means. That means that deep learning is here to help find genuine astrophysical events and objects among all those data. Before I jump into the DL part, let me briefly mention 2 tools that we're using in our deep learning efforts. The first one is called Kowalski, and it's kind of a Swiss knife system that we're using internally for time domain astronomy efforts with ZTF. But its main application that's relevant here is we're using it to store and access ZTF alerts and also light curves. It comes with an API and a Python client, and it has something like 100, at the moment it stores about 115 million ZTF alerts, 2.5 billion light curves. And it comes with this nice GUI, which we call ZTF Alert Lab, where you can efficiently and fast filter, display alerts, and access the stuff that's inside particular alerts. And another tool I'd like to mention we call Zwickyverse, that we use to manage and label large amounts of image data in a collaborative manner. Also comes with an API and a Python client. To the DL part, I'm sorry. The first system that I'd like to talk about, it's a real bogus classifier for ZTF, deep classifier. We call it BRAI, which stands for Bogus Real Adversarial Artificial Intelligence, or adversarial meaning bogus versus real. It's a CNN-based architecture, pretty boring one. I show it here. It's enough to solve the problem. It feeds off stacked triplets, so assigns like an apical image of the sky, a reference, and a difference image. And the task is to separate reals from boguses. This is a bogus, it's a bad subtraction, an example of a bad subtraction. At the moment, we have something like 30,000 training examples. All of them were pretty much looked at, and we tried relying to, say, citizen scientists, for instance, but as it turned out, they're really good at identifying real reals, but on the bogus side, people actually tend to call lots of things that are actually real boguses, or something like 30%. And so we used Zwickyverse for labeling, and it's trained on the GPU. And we also use active learning, so we look at the misclassifications and predictions of a particular version of the model to fix labels. But now the contamination, I would think it's at about a couple percent, the training set. Data mostly comes out of Kowalski, so we query it to sample the vast parameter space of ZTF alerts. And also ZTF transient and variable marshals are an invaluable source of data about the real objects. And some small chunk of the data also comes from Zooniverse. We're mostly using that for testing purposes. A couple words on the data diversity. Overall, it's pretty good, so to say, but there is still room for improvement, mainly in the galactic plane, shown here, and in the I band. But even there, the performance is pretty much state-of-the-art already. And my slide is about that. So this is a confusion matrix, and these are the score histograms. So if you set up the threshold at 0.5, you get something like 1% false negative rate and closer to 3% false positive rate. And just to demonstrate that, so for one particular night, I pulled out all the alerts, all the objects that were marked as reals on the growth marshal, on the ZTF transient marshal, and computed, so none of them were seen in the training, and so computed deep RB, so BRI scores for that, and compared that with the currently deployed random forest-based classifier, and you see the random forest classifier is in blue, and this peak at 1 is BRI. So it gets something like 0.3, 0.5, 0.7, depending on the night, percent false negative rate. Like a really cool thing that we recently did, so we actually took that model and compiled it to be run on this new type of machine learning centered, so to say, machine learning oriented devices called edge TPUs that Google sells for $75. And so you have to do a couple tricks. So the first one is you have to train your model. You have to do what's called quantization aware training, but whatever. So basically you get the same performance. There are a few caveats, like you get slightly less granularity on the score, but you don't really care whether it's 0.92 or 0.93 after you set up a particular threshold. So basically you get the same performance, and it takes something like 7 to 10 minutes to process the full night worth of ZTF alerts on this device plugged into a $35 Raspberry Pi. So, which means that we can do LSST scale alert stream processing in real time. And we experimented with different models. So as I mentioned, that one's pretty simple, but ResNet's still, you can do that too. So imagine having like 20 devices like this running different sorts of model for that, and you don't really need a GPU or anything more expensive than that. Switching gears a little bit to the solar system. As I mentioned at the beginning, the pipeline spits out something like 10 to the 5, 10 to the 6 streak candidates, with the vast majority of them being bogus ones. And the machine learning classifier that they originally used was also a random forest-based one, which only reduced that number by an order of magnitude, which is good but not so good, because that meant that people still spent like several hours a day looking through all those streaks. And the task was to reduce that dramatically while keeping the same false negative rate. And so we came up with this slightly more complicated architecture. So we split the task of identifying plausible streaks that come from real fast-moving objects into 3 simpler subtasks. The first one identifies all streak-like objects, which includes like long streaks from satellites and cosmic rays, and in addition to the actual FMOs. Then the second part decides whether it's a long or a short streak, and the last part decides whether to ditch or to keep it. Again, we used Zwickyverse to label the 30K training examples. So this is just an example of how the bogus things look like, and the task is to find these guys. And we get something like 96 to 98% true positive rate, depends on the night. And we quantified the performance both on the test data sets and using known news. So on this plot, I show all the news that we know were observed by ZDF in October 2018, January 2018, and out of them, 96% were successfully identified by deep streaks, this system. So as mentioned, it's below 1% false positive rate most of the time. Gets down to 3-4%. I'm sorry, true positive rate, and for false positive rate, it's well below 1%, which is something like a 50 to 100 times improvement over the original random forest classifier, which means that they were able to switch to pretty much near real-time operations, and they have to spend typically something like 5 minutes a day compared to literally hours that they had to do previously. So far, it's found over 30 new near-Earth objects, and something like the same amount was lost, because we're not the only ones who were hit by bad weather this year. And I'll stop here.
Thank you.